about momentum, we've talked about impulse, we've talked about the impulse momentum theorem, and now we're basically going to put it all together in this idea of conservation of momentum, which we've also mentioned earlier. And so I'm going to go through one or two just really basic conservation momentum problems that will kind of show you how these are all set up and hopefully give you a good idea of how to apply the law of conservation of energy to physics situations, which are usually collisions or explosions. So I'm going to do some very detailed drawings, all right? Detailed drawings. So here we have an object that I should draw using a pen. Check. Okay. Object, and picking a mass. Let's go with like 25 kilogram mass. And let's say it's, it's like a car, one of those cars that you're driving. And so it's going here at about 5 meters per second. All right. And then because it's going so fast, it's actually going to catch up and it's going to hit a 30 kilogram object that's going to the right. All right, at 3 meters per second. So it's going a bit slower. So that's how the 5 was able to catch up to the 3. All right, and this is what happens before. But all of a sudden, eventually, it's going to run into it, and then it's going to hit, and it's going to lock together because, I don't know, Velcro or the bumpers got connected. I don't know, but they're going to get stuck together. So we've got 25 kilogram, and then it's now attached to the 30 kilogram. All right, and so now we want to know, okay, so now they're stuck together, so how fast will they now be moving? All right, this is the type of stuff they actually do. They'll like reverse engineer it and say, oh man, you got in a car accident. Well, according to these skid marks, you were going this fast because they are using the law of conservation of momentum. So you always kind of draw this. You always draw a before scenario, so it's like before the collision, and then you draw the after scenario, what happened after the collision. All right, and that's kind of something that separates the two sections. So we're going to use the law of conservation of momentum to solve for what is the final velocity of these objects now that they're stuck together. So here's how I write it. I say if you add up all the momentum before the collision, that's going to be equal to all of the momentum after the collision. Okay, law of conservation of momentum. No momentum was lost. All right, so whatever total momentum you had in your system before the collision, it's equal to the total momentum that you have after the collision. So now I just have to basically say, okay, well, what had momentum? So here I have two objects. So I could do like momentum 1 plus momentum 2, but that takes too much time. So I say, okay, that's momentum 1 plus momentum 2, because momentum is mass times velocity. And then at the end, we only have one object. So we have one object, and it's got one velocity. So now I'm just going to throw everything in where it goes. So here I've got a mass of 25 kilograms. I've got a velocity of 5. And I've got a mass of 30. And it's a velocity of 3. And now I've got the only one object, so its total mass is 55. And I want to know, well, how fast is it going? So now all I have to do is the excitement of algebra. All right, so I'm going to clear that up, just a little cleanliness. So if you crunch your numbers, you do your algebra right, hopefully I did, I'm sure you did, then you're going to get a velocity that is equal to 3.91 meters per second. So you can say, oh, well, since they stuck together, I can keep track of all the momentums, and then I can figure out, okay, how fast are they going afterwards? All right, so this is just one example of a law of conservation of momentum. All right, so we call this a hit and stick problem. All right, so we have what's called an inelastic collision. So they hit together and nothing really happens. So they just stick together and they move off at different speed. So that's one type. Well, here's a different scenario. We're going to take the same setup and we're going to take the exact same cars just as they were. All right, so we have, again, our 25 kilogram, and it's still moving. I really probably should just erase the whole thing and start over, but I think that I feel like I've crossed the Rubicon on that one, so no going back. Might as well just redraw the whole thing. So again, I'm going to do the exact same scenario, except I'm going to do something a little bit different, and I'm going to have it so that they are going to stick together. I'm sorry, that was last time. I'm going to have it so they bounce apart. There's my brain. All right, so before, same setup. All right, one car is catching up to the other car. And then afterwards, now they're going to not stick together. I should put a 25, not 2 kilogram. Whoop. All right, so 25 kilogram. And then they're not going to stick together, so they're now separate. All right. So this guy, let's say afterwards he was still moving at 2 meters per second. All right. So this is the after scenario. So it's a little bit different than the before. And so now we want to know, okay, so how fast is the 30 going to be moving after this? Well, we use the exact same approach. Okay, momentum is still going to be conserved in any collision. So the total momentum before the collision is going to be equal to the total momentum after the collision. Well, here we have two objects before the collision, so we have to keep track of each of their momentums. So mv plus mv. And then afterwards, we again have two objects. So equals mv plus mv. Now, this is why I always draw the picture, and I laid out very specifically where I got my little line here equals the equal sign, the before stays with the before, the after stays with the after. So this way I don't have to keep like 1,000 subscripts. All right, so you can have 1,000 subscripts if it makes you happy, but whatever allows you to keep track of it, that's what's important. So now I'm going to punch in where it goes. So here's my first object. So I've got 25 times 5 plus second object 30 times 3. And then over here, now we're in the after, so we've got 25 times 2 plus 30 times v. And so now, at this point, all that's left is algebra. So I'll crunch all my numbers, and I'm going to get 5.5 meters per second. So in this case, instead of hitting and stuck together, it hits, it bounces off, so this guy actually has a different velocity than this guy has, and you can still calculate using the exact same method. So I mean, if you go back up, this work looks basically identical to this work. The only difference is in this one we had only one momentum at the end because there's only one object. Here we had two, but basically the exact same problem. Okay, so these are your basic introductory conservation momentum problems that should get you through the vast majority of the situations that you'll be faced with in class. So hope that was helpful, and I'll catch you on the flip side. Bye.